Hello, today I'll explain to you why every human on the planet would be a fish if fish existed, which they don't, together with this Tiktaalik. But before I explain this classification, you're going to need to learn a little bit of terminology. After all, this is biology. Cladistics is a system of classification for organisms based on their evolutionary history, informed by studying their physical characteristics, genetics, and the fossil record. It was developed by German biologist Willy Hennig in 1950. You may have heard of the more traditional Linnean system of classification, which sorts organisms into increasingly specific groups. Cladistics does this too. However, the Linnean system artificially ranks these groups into 8 tiers, which are from largest to smallest: domain, kingdom, phylum, class, order, family, genus, and species. Cladistics does not do this, although it does use genus and species, and not artificially ranking groups is one of its advantages over the Linnean system, as this can be misleading. For example, the family Ailuridae, the red pandas, contains 24 known species, both living and extinct, and the family Coccinellidae, the ladybugs, has over 6,000 described species. Both are classified as families, despite ladybugs having several hundred times more known species, even considering their sparse fossil record. The cladistic classification of organisms is displayed on a diagram called a phylogenetic tree, which is sort of like a family tree, a branching diagram that represents the history and relationships of groups and species. In this video, I will be using cladograms, which are a type of phylogenetic tree that does not display time along one axis, for simplicity, as time will not be relevant here. To help understand why fish don't exist and why we would be fish if they did, you're going to need to learn how to read a cladogram. This is a very simple cladogram of mammals. At the top, you can see free organisms: kangaroos, humans, and cats. Each sits at the end of a branch of the cladogram, and as you follow the branches down, you are following the evolutionary history of these organisms back in time. Basically, you're following their family history really far back. If you trace back the branches from multiple organisms, the point where they converge is called a node. It represents the last organism that was a direct ancestor to all the aforementioned organisms. If you're a bit confused, remember that you can think of it as a family tree. If you trace back the ancestry of you and your first cousin, you'd find your parents and your aunt and uncle before finally reaching the last people who are direct ancestors of both of you: your grandparents. Your great grandparents would be the direct ancestor of both of you as well, but since they lived longer ago, they are not you and your cousin's most recent common ancestor. As you can see, there's another node, an older common ancestor, that can be traced back from humans, cats, and kangaroos. All these organisms share common ancestors, but cats and humans are more closely related because they shared a common ancestor more recently. This means that humans are more closely related to cats than either of us are to kangaroos. Kangaroos are equally related to both cats and humans because they shared a common ancestor with us equally recently. Any common ancestor of both kangaroos and humans must also be a common ancestor to cats, and any common ancestor of both kangaroos and cats must also be a common ancestor to humans. The free names to the side of the cladogram, Laurasiatheria, Eutheria, and Mammalia, are the names of free phylogenetic groups. We'll get back to these specific examples, but first I'll explain the free types of phylogenetic groups. Number 1. Paraphyletic groups. Let's say you were looking at this mammal cladogram. You decide to make a group that includes the common ancestors of kangaroos and cats, and all that common ancestors' descendants, except for humans. This group would be paraphyletic because it includes the common ancestor, but not all of its descendants. Next, let's say you feel bad for leaving the humans out, so you decide to make a new group that includes them, but in exchange you leave out the common ancestor. This group would be polyphyletic because it includes several organisms, but not all their common ancestors. Finally, you decide that you want to make a new group that includes all the organisms: the kangaroos, the humans, the cats, their common ancestor, and all its descendants. This group would be monophyletic. Monophyletic groups, also known as clades, are almost exclusively used in cladistics, with exceptions of course, over paraphyletic and polyphyletic groups because they show us the complete evolutionary history of the organisms grouped in them. Non-monophyletic groups are usually rejected in this system of classification. A specific clade can be defined by stating that it includes a common ancestor of two organisms and all its descendants. For example, the clade Dinosauria is sometimes defined as the common ancestor of Triceratops horridus and Pastor domesticus, the house sparrow, and all its descendants. Coming back to those free groups on the side, Laurasiatheria, Eutheria, and Mammalia, these are all good examples of clades. They are placed where they are on the cladogram to denote at which point everything after them is a part of them. Going back to the family tree analogy, these names would be separate groups that you drew inside your family that get more and more specific. So in this cladogram, everything after here is a Laurasiatherian, everything after here is a Eutherian, and everything after here is a mammal. This means that every Laurasiatherian is a Eutherian, and every Eutherian, and therefore every Laurasiatherian, is a mammal. Now you know how to read a cladogram and understand a little more about phylogenetic groups. I will finally explain why humans are fish, or at least would be if fish existed. This is the smallest cladogram of everything that would normally be considered a fish. These names at the top are not actually organisms, but other clades, which does not change the meaning of this cladogram, it's just more useful in this case. Just imagine that there are smaller cladograms branching out from each of these names. From left to right, there's Cyclostomi, a group of jawless fish, such as the modern-day hagfish, Chondrichthyes, the cartilaginous fish, like sharks and rays, Actinopterygii, which includes pretty much everything that you think of when you think of fish, from the fishiest fish, like salmon, cod, and sardines, to weirder fish, like sailfish and seahorses. Actinistia, a once more diverse group that now only has the two extant or living species of coelacanth, Dinoi, the lungfish, and finally, Tetrapoda, the group that contains amphibians, reptiles, birds, and mammals, including humans. There are some smaller clades that are absent here, but they are not relevant to this video. Now, if you were to draw a line around all the groups that would normally be considered fish, it would look something like this. See the problem? This group includes a bunch of clades and their common ancestor, but it excludes the tetrapods, which means that this group is paraphyletic, and as you now know, that's something to be avoided. You could decide that you really want fish to be a monophyletic group, a clade, and that you're fine with tetrapods being fish so long as the others are too, but this group would basically be the same as vertebrata. You could go the other route and decide that you really don't want to be a fish, and that you're fine with a monophyletic group that includes as many of the most well-known fish as possible without including tetrapoda, but then you'd basically be remaking Actinopterygii. And look at everything that's being left down. Are you really willing to walk up to a great white shark and tell him that he's kicked out of the fish club? And another thing, you remember how to tell which organisms in a cladogram are more closely related together? If you trace back the branches from humans, tetrapoda, salmon, Actinopterygii, and great whites, Chondrichthyes, to where they converge, humans and salmon shared a common ancestor more recently than either of us did with great whites. You are more closely related to a salmon than either of us are to a great white shark. This may all seem a bit far-fetched when you compare a human to a salmon, but when you compare a salmon to a coelacanth, to a tiktaalik, to a non-amniote tetrapod, to a basal synapsid, to a derived synapsid, to a basal mammal, to a basal urocondylar, to a basal primate, to an ape, to a human, you can see the resemblance. And keep in mind that that's just a few organisms from the 400 million year transition from fish to people. A quick disclaimer, none of these organisms were direct ancestors to humans, they're just to give you an idea of how this transition happened. I hope that now, with your newfound knowledge of phylogeny, cladograms, and vertebrate evolution, you can see why fish aren't considered a valid taxonomic group, and why, if you were to make them one, humans would most likely be a part of it. However, I do still think that fish is a useful term, as ecologically, culinarily, and even anatomically, fish are clearly distinct from other vertebrates. My point is simply that they are not an actual scientific group.